Good morning, everybody. Today, in the series of Thursday lectures, we have a very eminent speaker. For a change, I would also be learning something new because I was trying to go through the subject that she is going to iterate for us, and I realized that I have no knowledge about it. And somehow it is connected with the defense industry, particularly aeronautic engineering. So we have Ms Rachna Harsh from Bangalore, who will be giving a talk to us on model-based engineering and product line engineering. So I'll request the speaker to keep the level of talk, to pitch it at a level that people like us can also understand who are non-engineers. Without taking too much of time, I'll request Vinayak to introduce the speaker for today.
Good morning, everyone. The speaker for today, Ms Rachna Harsh, is an international authority on model-based systems engineering, MBSE, and product line engineering, PLE, with career experience spanning across aerospace, defense, and automotive industries. With a master's in system engineering from Central Nantes and a dual bachelor's in aeronautical engineering from Hamburg University of Applied Sciences and Weltech Chennai, she combines academic rigor with global industry practice. Ms. Rachna Harsh has contributed to projects at BAE Systems and Kalyani Defense, including an air defense system for the Indian Army, and now leads a global solutions consulting team at PTC, driving aerospace and defense accounts worldwide. A frequent presenter at international forums, she has associated with Lockheed Martin, Northrop Grumman, and Mahindra, while actively contributing to INCO's PLE working group. Beyond the professional sphere, Ms. Rachna Harsh is a polyglot, a lifelong learner, and proudly represent Bharat's dance heritage at international cultural exchange programs. We welcome you, ma'am.
Thank you so much, everyone, for the warm welcome. It's really a pleasure being here and to be able to present here and talk to all of you. I will just quickly share my screen here, and please let me know once you're able to see it. Yeah.
Yeah, visible.
Okay, thank you so much. So today I would be talking about the concept or the methodology of systems engineering first. Systems engineering is something that now we are globally handling and looking at in COSI, which is the International Council of Systems Engineering, headquartered in North America, but every country has its own chapter. So this organization is essentially responsible for putting down all the standards about how a system should be developed in a certain way that everyone involved in it, they're talking the same language. So I will give you more introduction to this once we get inside the presentation. And secondly, the part where we are talking about product line engineering. So product line engineering is where we try to explain that no organization today is building just one product. Because if we want to stay relevant, we have the different variants of our product being used for different capacities. And how can we treat all of this together, and why should we treat all of this together is going to be the focus today. And I will try to bring in points that I have noticed based on the experience that I've had when I worked with BAE and Kalyani here in India, and the global aerospace and defense companies that I've been working with. But your suggestions, questions, comments are all welcome. So these are some of the identified topics for today. So we would start with the context and the motivation. Why is this important? What are some of the challenges that I have realized by speaking to several people here in India in the industry, then to introduce the concept of systems engineering and product line engineering, talking a little bit on why model-based product line engineering or MBPLE is important in the defense sector, what the global implementations look like, and some of the Indian specific use cases that I have come across. And then at the last, we just talk a little bit on what the proposed framework could look like and the implementation roadmap. So let's start a bit on the motivation. There are certain strategic imperatives of Atmanirbharta under several programs which have been talked about as, for example, DAP 2020 or DPM 2025. And I'm sure all of you are more aware of what these are as compared to I am, but this is what the motivation was. And then the global trend that the defense industry is now moving from ETO to CTO. Now, what exactly this is for a very long time, the defense industry has been working on engineering to order perspective. Everything is built from scratch for every other program. We are getting the requirements. It could be similar to some of the other programs as well, but we are trying to do everything from scratch. We get the requirements, we try to figure out what the implicit meaning of these requirements are, and then we start building the entire system. So this entire process is very expensive in terms of money, is very time taking in terms of the fact that if I have engineered something already today and I get the requirement from another part of the military, let's say Navy, previously I got it from the Army, but I would start doing everything from scratch, which eventually takes a lot of time and a lot of money to finally give it to the end user. So the pattern is now seen that they're moving from ETO to CTO. CTO is configure to order, which means I'm not going to do everything from scratch, but I'm going to look at the problem statement provided to me, and then I will provide you with the existing possible solutions with some customizations to it. So I will not customize 100%, but I will have parts of it which will be customized so that I can meet your pain points or the solution that is required. So this is a global trend that has been seen in this industry. And thirdly, what improvements can we make in the current program execution patterns, which is very much related to the second point, because it's a whole shift that we go from one way of working to another way of working. And when we do that, the improvements that we see at the end of it is we have more time to really think about innovation, to think about design, engineering, making the existing processes more efficient so that we are able to deliver faster. So it has a faster time to the market. And innovations are not taking that long. So years of innovation, this is not what it's taking. So we have a lot of scope of improvement if we shift the processes as well. Then moving on, some of the identified challenges. One thing that I have noticed or seen while I have been working with organizations globally, that these challenges are not just India specific. There are a lot of companies, whether we talk about the automotive sector, if we talk about the aerospace, defense, the medical technology, all of these are facing similar challenges, whether it's with regards to the processes of how this is working or really just focusing on the engineering sides as well. So the first one is definitely that with the documentation practice, right? So let's say if I have to design a system which can be used by Army, Navy, Air Force, other hands of military, maybe something that can have a commercial use as well. Today, all of these are separate ones, because for building any system for any one of these applications also, the documentation practice is in place, which means I can write a document the way I understand it, but you could write it the way you understand it. In the sense, I would come more from the engineering perspective, but you will bring in the process perspective. So nobody's speaking the same language. Everything is very fragmented, siloed. So therefore leading to the non-standard architectures. And this is the reason why we have the systems engineering methodology. One organization that controls it talks about the standard. So at the end of the day, both you and I can speak the same language. The second one is the vendor lock-in due to the proprietary systems. So we had this challenge when I was previously working, is if I have to buy from you, then any little change that I would want in the system to happen, just because it would suit my use case or challenge better, I have to always keep going back to you. And why is that? It's because we do not share a common practice of how things can be implemented. I have to be completely dependent on the vendor who is providing me with that system or with that solution. And therefore, this is a very big challenge, because at the end, there are two things which happen. Either the change that I want is very critical and you agree to make the changes, but it comes at a very big cost, whether it's time or money. And the second thing is, we look at the cost factor or the time factor and agree that I will work with whatever is available. So somewhere there has to be a compromise, because we are not having a standard way of or a standard methodology of approaching something. Then next, and a very common one, irrespective of the industry, is the clone and own approach. And this has also been seen even when I was previously which was my first project here that I was involved with, which is we had a system that was essentially developed for naval applications. And then we wanted to use that for the land operations as well. But there was a high amount of clone and own, which means the entire system architecture, the entire system design, all the requirements, the test cases, everything had to be copy and pasted. And that leads to a big amount of rework. And if I had a modular approach in place for this kind of reuse, I would have been able to do the same thing in much lesser time. And the customization which is required towards the end to see that this fits the land operations better and this fits the naval operations better was really not there. There were a lot of I wouldn't say compromises, but settlements that we had to do here and there, because everything was clone and own. So that is another challenge which we have largely in all industries. And then the late requirements that come in from the SHQs. It's not really like they want to give us the late requirements, but it's really that sometimes they learn about something towards the end, or while working with a specific system, they realize, okay, we could also add a certain something to the existing system, which can make life easier for military. And having this late requirement come in, sometimes when we are following the engineering to order process, or when we do not have a standard methodology in place, brings a lot of work with it. And therefore, if I am somebody who's building the system, would at the end get very frustrated by it, that there are so many last minute requirements which I have to deal with. But at the same time, if I'm looking at it from the military perspective, this is really necessary for them. So again, if we have a common methodology, a modular reuse approach to work with, we can very well deal with these late requirement, that is all these late requirements which are coming to us as well. And then the very important point is that we have limited systems engineering adoption in the research and development as well as the production phases. And something interesting that I noticed is, we say that India in general has a very limited adoption of systems engineering, but I do not completely agree to this, because yesterday, day before, I had some meetings in India who have the offices over here, or I would say the center of excellence that they have over here for the organizations in US. And all these people sitting here have amazing knowledge about the systems engineering methodology, how this is supposed to work, what the language is about, everything. But the factor that it is coming or being defined from another country and they are following it is one thing. So I think we have all the knowledge people over here as well who can then bring this kind of systems engineering methodology for if we are using it for research and development as well, because things would smoothen out a lot. And lastly, as I already described, the low reuse of subsystem designs across the different platforms. It is really not required that I treat every requirement coming in from a different hand or a different arm of the military as a separate one and work in silos. There could be a very good integration between the different arms, and the results will really be that we are able to reuse what was already there. And the siloed mindset, if that is removed, not from any organization, right? Not just defense, but in this case, since we're talking about defense, the moment we do not have this siloed mindset but we talk about this is a central repository, a central space where we have everything, and then whatever is required, we can reuse, and the rest of the stuff can be customized. That will make life easier for everyone. So therefore, that is another challenge, that there is very little reuse of the existing systems or the subsystems. And then the answer to all of these challenges comes from this methodology. So this is a very engineering specific diagram, but I just wanted to put in here to let you know that this is something that is coming from INCOSE, as I mentioned before, the International Council of Systems Engineers. And India also has its own Indian chapter, and they are doing very good in supporting. And I learned that they're working with DRDOs, ISRO, different DRDO labs, ISRO, then different companies, Indian companies that are supporting the military for the products and systems that they require. So what essentially this whole thing is trying to talk about over here is, on the left-hand side of this V, we are trying to decompose the problem statement. Whatever is asked for, we try to decompose it, break it down, because one system that needs to be delivered can have several subsystems. And together they should be working in a way you get the results that you are hoping and expecting. So this left-hand side of the V is really talking about the decomposition, whereas the right-hand side over here is where we get to the integration and the realization phase. So everything that we had decomposed, we try to bring them together and see whether we are getting the same results or not. Now, the interesting thing over here is, when somebody is doing that, everybody who is working based on this V is learning a specific methodology. So they are talking in the same language with regards to a specific word can have several definitions. For you, it could mean something else. For me, it could mean something else. But in this case, we try that everybody is talking in the same language. They have similar ways of how they can treat requirements coming from different customers or different projects in a way that can have modular reuse later on. So there are several benefits of what happens when we follow something of this sort. And then one noticeable thing is, document-based systems engineering exists even today in small bits and pieces for every organization or within every organization. Because if I'm a customer, I'm giving in some requirements, and everybody has their own ways of breaking down these requirements so that at the end of the day, they are able to build the solution that I require. And this is what I spoke about before as well, that this is a very siloed approach, because there is one person who's only looking at these requirements, and anything related to that requirement changes later on. The entire process has to be very manual. It is from one organization to another part of the organization to say that, see, something has changed. And then they have to go and talk further. So there is no one way how anybody at the top is able to view that, okay, I had a problem over here. This requirement changed, which led to this and this and this change, right? Why the result is looking different now. So with the help of model-based systems engineering is how we are able to achieve that. So under systems engineering also we have the document-based approach, which was followed for a very long time, and then the drawbacks realized, and then we came to the model-based systems engineering approach, which means everything that you are talking about right now is all in the form of these blocks and models, which makes it easier for somebody really at the component level, deep within the engineering side of things, to look at as well. And also someone who's at the top, who just needs to see like what this architecture looks like, what all does it contain, what the simulated result looks like. We are able to achieve all of it when we go ahead with the model-based systems engineering. It includes a specific language that we call the system modeling language, and there are several tools on the market that help us implementing that. So this is why MBSE is really an integral part once we start designing systems, building systems, and how in the long term we can maintain that even when evolution comes in or some part of it becomes obsolete. And this provides us the framework for the next part, which is product line engineering. Again, this is coming from INCOSE as well. I'm a part of the PLE working group also at INCOSE. So this is the place where we are really talking about all the different needs, challenges, problem statements that we have understood from customers, working with them globally. We talk about those within these working groups and see what standards can come in, which are in a unified way solving the challenges across the different organizations, irrespective of the sector they are. So if I just simply try to explain you something over here, if on the left-hand side you see, I have the V that I showed you before. Put in very simple terms, every product or every system that I have to build will have a V of its own, right? And this is what I would not want to do in the long term, which means if I take a very simple example, right? Mobile phones. Every phone has its own series. And it's not like one is drastically different from the other one. They do have some changes, but at the end of the day, I can very simply put that this series of, or this iPhone is a variant of the existing one, right? So instead of treating all of these developments of different mobile series as a separate project in its own, I will try to treat them as one family. So when I treat it as one family, at the end, I can have all the different small V's which are coming out of it in a branched out format. So essentially what I'm trying to say is, very simply put, in order to have efficient engineering, in order to have a lot of time, space to think about innovation, to think about what will the evolution of this specific system look like, so that I can have a future or a forward thinking mindset to sit with you and to talk about the challenges, and then also not to spend a lot of similar money for the development of each of these. I can really reuse from the existing one, and I will not have to put in the same amount of money to do something that I've already done. We have product line engineering into place, where everything that belongs to one family of product, I will treat them as one instead of looking at each of them as a separate project. So simply put, this is what product line engineering talks about. And therefore, we have a way how we can join both of these methodologies together to say model-based product line engineering is the methodology that can support any industry working on mechatronical systems. Not just that, but how it can also accelerate the existing organizational processes, the way it works, and how to make things more faster and efficient, in short. So then we look a little bit and talk about the importance of MBPLE for defense specific applications. If you look at the first point, it says increasing number of variants, which is true, right? Because I cannot build just one system and expect that I would stay relevant throughout. So I have to build different variants of this for different applications. Something that I worked on before, right? The air defense system. We had the naval operation. It was used for naval operations as well as it had land operation applications as well. So these are essentially the variants of the same product. And if I'm treating both of these as separate ones altogether, what is happening is now I have a lot of time, effort, resources, money that I'm putting in to maintain at least 70% similar assets, similar processes. Instead of having to spend 2 times for it, I can just have a central repository where I can maintain all of these together. And the only parts which need specific attention are the ones which are different. The rest 30%, which is different because it's the naval side of things or the land side of things. So increasing number of variants, this variant explosion, it leads to us considering every variant as a new project, which means the entire cycle goes up like that. And then, of course, in the future, the cost of fixing something that needs to change, or the requirements that have now been evolving, or certain features which have now become obsolete. So all of this together can be managed if we have MBPLE in place. Then the second one, the configuration explosion due to mission specific needs. Now, uh, imagine if you had the option that there is a tree like structure where you can just pick up, I want this, I want this, I want this. And then I'm able to give you this system built in a very short amount of time rather than taking 4, 5, 6, 7 years to do something like this. This is what MBPLE helps with. It tries to control everything in such a way that for you, who's the end user of it, you can just have like a something that we have when we go to buy a new car. We can say, I want this feature, this feature, this feature, and they say, here is the car that you want. It is something similar that we can do in this case as well. So as an end user, you can just tell me, I want this, this, and this feature because my mission specific needs are so and so. And therefore, I know that now I have 20% customization to the existing system because this mission needs these properties or these features. So this is something that is highly manageable if we have the model-based product line engineering methodology in place. And then thirdly, talking about the fact that it enables modularity, openness, and standardization, which means today, if I'm talking to another organization, someone in US or someone within Europe, we are now talking the same language. We do not have the problem that they have a specific standard, they are working according to that, but we might not be knowing the similar terms, or we do not have the openness or the modularity which is required for it. All of those challenges can be solved. And as I mentioned before, it is not like that these challenges don't exist in Europe or USA or Japan, South Korea today. They still do. And even though methodologies are coming in from there, they have high knowledge of this, they know what the implementation could look like. But still, it is a challenge over there as well. Today, a lot of their information exchange also looks like Excel sheets, which is really not required. Like we can have a proper way how to have a central repository and maintain this modular reuse approach and the openness. And lastly, the alignment with the Ministry of Defense's emphasis that we should have our own IPs in order to be able to also do rapid upgrades, right? So, because this was just my personal experience when I was here, that even when we wanted to change a small component, there was a huge verification validation cycle that came along with it. Not because India was not able to do it, but because we had this vendor lock-in situation that we had to be highly dependent on the vendor, and they themselves had some parts of systems engineering methodology implemented because it was not complete. So they thought changing even one small component would bring a huge cost to them in terms of testing everything again, which essentially was not required. But also at that point in time, I did not have the knowledge I have today. Otherwise, maybe things would have been different. But implementation of MBPLE also aligns with the existing vision that our Ministry of Defense has. And then I can talk a little bit about the global implementation, some places where I have supported this and we have seen the results as well. Lockheed Martin, Northrop Grumman, some of the organizations within US, where I have extensively worked with them for such a methodology implementation, because the challenges were very similar, as I said. And one of the interesting things, or just my observation, is that it's very easy for us to, for the Indian defense, to really go and start with this, because we are not trying to unlearn and learn something new. In the sense, I do not have a specific way how I'm using systems engineering today, that I might have to unlearn certain aspects or some ways of me working and then put in something new in that. It is really like I can go from having not implemented this to implementing it the right way and be faster and more productive. So just an observation after working with some of the organizations. And if we come to the European Union, there has been now enterprise level of PLE implementations within the automotive sector. I'm not sure if I can name them, but if I say this, I'm sure you are able to guess this, is some of the top organizations within Germany for automotive. They have an extensive implementation of model-based systems engineering and product line engineering. And some other accounts that we have worked with, and I'm also currently working with, like Airbus, Thales, Honeywell. They also have publicly available examples of how and what was that pain point where they came up to the realization that model-based product line engineering is the answer. And this is something that needs to be implemented in there for sure. So some of the results that they have been able to see with this implementation has been the way where I said we are moving to this configure to order sort of a situation. So they have been able to achieve the faster time to market. They have been able to achieve lower redundancy and a higher reuse of the existing system architectures which they have. Because if at all I have to build a system which is drastically different from the other one, of course I will do everything from scratch. But if I know that the next system that is coming to me has at least 60 to 70% reuse of what is already developed and engineered, that is exactly when I know that model-based product line engineering can support me to a really great extent. And something that I came across while I was reading, and the first one is definitely that I have some experience on working on as well, are some of the Indian specific use cases. And of course, the list, this is not exhaustive, right? The list is huge. There are several ways how to, or several different systems that we can consider where this can be implemented. But like the air defense systems, the UAS platforms, the digital signature systems are all the ones where I know that one product or one platform in itself is not going to be enough to satisfy every mission need or every different requirement which is coming from the end user. So these are exactly the use cases where I can say I have one central repository where I'm storing in all the different needs, requirements, system design, architecture, everything that is required. And then what I'm simply going to do is with the implementation of model-based product line engineering, I will be able to branch out something from this central repository to say this branch has everything that is required by Air Force. This branch has everything that is required by the Indian Army, or this branch has everything that is required by the Navy or for the naval operations. So this is essentially the whole idea. Rather than treating all of these different arms as a separate one, I treat them as one family, one central repository, and the different branches coming out of it. So that at any point in time, something new comes up which impacts all the three different branches, then I can just go back to my central repository and add everything over there. And then this will flow to all the different branches which have now been generated, right? And if there is something which is just specific to, let's say, the Indian Army, then I don't have to go to the central repository. I have a separate branch. It can continue to exist on its own, and I can continue to work with what is there already. And then this is what a framework that I think, based on my experience, is where we can start with. Of course, there's a lot more to do with it, but these are like the basics of where we can start with today. Is, as I said, to establish a unified superset repository. It's like a superset because it has everything that is common to all the different branches which needs to use it, and it also has the non-common aspects, which means this one is only supposed to be used by land or only supposed to be used by air. So we create such a superset repository so that we are able to treat it like one family. And as an example, for land, maritime, airspace, cyber, several applications for it. And then common interface standards. So when we are talking in the same language, it's easy for all the customizations which we have to make to check if something needs to evolve over time, because now we need newer ways of tackling similar problems. Then, of course, the variability models. So the different variations that we need, something that is capability based, something could be terrain based, something could be mission based. And I don't have to treat all of them separately. Like I can treat them as one and say, okay, the customizations appear because the terrain looks like this, or the capability needs to have these existing features and maybe two more. And then to talk about the shared verification and validation processes. So if we recall the last a couple of slides behind when we saw the V for systems engineering, if we are able to go through that process, then we have the shared ways of verifying and validating whether the assets which exist are giving us the results that we expect. So this really could be reusing the existing models, reusing the results of the test cases or the simulators that we have already tested, because it already has what you need, and now I will add something more to that. And lastly, when we're talking about the traceability, because if we work in a siloed manner, the traceability is not possible. It's not possible for me to say that because a requirement change was requested in this phase, that is why the test over here needs to be different, because everything is very siloed. So everyone is only going to work on the basis of, okay, this is asked for, this is requested, so we are just carrying it out. But for you who's sitting at the top level to really see, can I trace it back? Like what requirement or what request coming in had changed, which is why it led to the change of this system in such a way, does not exist if we are not working with a traceable methodology, right? In a manner that I have this central view of everything together. And then a little bit on what the strategic and the economic impact of the implementation of such a framework could look like. The number one factor is the low program cost and risk, because every program, if I treat that like all the different systems which are coming within a specific program, and all these different systems are just variants of one another. If I'm treating all of them as separate projects, it's like every time I am investing X million rupees in there. But that is not really required, because if I say two different systems under this specific program are 80% similar, that means 80% work is not supposed to be redone. I can just take it and reuse it from the existing space. But since I'm not able to do that, both of them are needing equal amounts of maintenance efforts, equal number of people who have to look at it. They need equal amount of cost which goes in it as well, and the risks involved with it also, right? So, if, as I said, if there is no methodology implemented, everything is very siloed. So this leads to a huge risk, because it could be that I changed a requirement, but the message was not passed on to the testing team in the in that specific time where they were going to run the test. So now they are testing the same set but for a changed requirement, which means this process will have to be redone, and that increases the risk of not having the system being delivered on time, or sometimes wrong tests done for the wrong set of requirements or the system architecture. And this is a very common problem statement. So therefore, if we have the MBPLE implementation, we can reduce this to a very large extent. Then the second one, where we are talking about the faster prototype development for evaluation. Again, bringing in the ETO and CTO concept. If I have developed the prototype for something one time. And once I have done it, I have a similar use case with 10% customization, which I need to send in for a proof of concept or some kind of evaluation. So for that specific prototype, I might not need to have a timeline of 2 years again, because we only have 10% customization. So I can really bring down the development time if I'm able to reuse and have a modular approach to building of my assets and then reusing them as well. And this implies that because I have reduced the time for the prototype development, it's really giving me more time now to think about how to make the engineering aspects more efficient. What would innovation look like? And this will really lead to more of indigenization, because our dependence would also reduce. Not in the starting to a large extent, but eventually over time we will see the results as well, because it's like we know our problems better, but today we have to work with the solutions which are available outside, because we need more time to develop something, and it's easier to buy a solution that exists already. So to solve this entire part, this is one of the strategic impacts that we can have by implementing such a methodology. And last but not the least, it also speeds up our export potential as well, because now we have more time to innovate, to think about how our product could look like, and then of course the variants of it which can be then sold, or which would then have the export potential for the other countries that we work with globally. And to one more time highlight or to talk about the alignment with Atmanirbharta, all the points that we spoke about before, the strategic impacts are definitely the ones that add to this one, but also the fact that now we would have our own IP accumulation. The competitiveness of Indian OEMs will increase with all the with respect to the global organizations, and this would also support the dual use innovation, in the sense, if I have a military specific product today, I can build the variants of these systems or products which can then be utilized by other sectors as well, because I can have some customizations. My subsystems could essentially remain the same, but the results that they're bringing in, this is the space where we could differ for sure, like based on the applications of automotive, for instance, or robotics. And lastly, the key takeaways that I can see from everything that we talked about, or I talked about until now, is that having the implementation of MBPLE is definitely going to accelerate our own capabilities for development, for engineering, for the space, for innovation as well. It's not like all these do not exist today. They do, but they are just fragmented. And as I said, it's not our country specific challenge. It exists everywhere, and everyone is trying to implement something or the other to make this better. Then the second one is it is going to drive modularity, reuse, and the standardization as well. So we will have more modular blocks of an existing system, which would be there, so that I can just say, I want to reuse this from this system and so from system two, so that I can have a new system that is developed for a mission specific application. Then the third one is to reduce the cost and time while improving the quality as well, because now the cost and time are reduced since there is a high possibility of reuse, and therefore I can really focus on improving the quality as well. So no compromises or no shortcuts that we have to take because we need to deliver something in a specific time. And lastly, it's definitely essential for the modern multi-domain defense systems, because every defense system in its own is very complex. So one person being able to handle something like this, or a team of people being able to handle something like this, is also very challenging and complex. But if there is one way how we can implement a centralized perspective to it, everybody has access to that part of the elephant which they really need to deal with. So for me, the conclusion really is that we, as I said, we can position ourselves in such a way that we can directly get into the MBPLE enabled defense development. Because we are not in a place where we moved away from the siloed framework and are trying to implement something, and now we need to stop implementing that so that we can implement the existing standard MBPLE methodology. It's really like we can move from one way of working to the other. And the second one, the national security demands engineering maturity. So today was like a very much overview of what these methodologies have resulted into. But when we get into the deeper understanding of what they are, it really will lead to improvements in the engineering processes, which will lead to the maturity. And as I said, it's not like the knowledge is not there. Currently, the knowledge is also a little bit fragmented. So if we make efforts to bring that together, it's like we already have everything we need. Just need to put the puzzle together to have the whole picture. And MBPLE has proven that it is the backbone for scalable, export ready, and future-proof systems, future-proof defense systems as well. So I would say future-proof any mechatronical system, or even the organizational processes, if they follow the same mindset of what systems engineering is trying to teach. Because systems engineering in itself is divided into several different branches. Something that is dealing with requirements, something that is dealing with architecture, something that is dealing with the organizational processes. It is already there. So when we go more deeper into it, we realize that it is really addressing every aspect, like end-to-end development of any system. So I think with that, I would like to bring my presentation to an end. If there are any questions or comments, opinions, please let me know.